Welcome to the deep dive. We're here to bring you the essence of really critical research. And today, well, we're looking at something that challenges a core assumption about large language models specifically, this idea that they inherently keep user data somewhat private just by processing it. You see, for a long time, the thinking went something like this. You type in a prompt, the LLM turns it into complex numbers, these hidden states in the latent space. And because of all the complicated nonlinear steps involved, like layer norm or activations, everyone sort of assumed this process had to be lossy, that different inputs might just, mush together into the same numerical state. And if that happened, getting the exact original text back, impossible. It was almost seen as a built-in privacy feature. Data goes in, gets mixed up, can't be perfectly unscrambled. But what if that's just not true?
Well, that's exactly what the research we're diving into today demonstrates. The core finding, rigorously proven, is that standard transformer LMs are almost surely injective, and that means they are lossless. The connection between your input and its numerical form isn't lossy, not inherently anyway. The information is all there, it's unique, and crucially, it's recoverable. So our mission today is to unpack this property injectivity, look at the huge amount of evidence backing it up. We're talking billions of tests, then reveal the algorithm, snippet that can actually reverse the process, and really explore what this means for privacy, for auditing, for regulations. It's quite significant.
Okay, injectivity. Let's start there. For you, the listener, what exactly does injective mean here? And why should you care about this seemingly technical property?
Right. So injectivity basically means it's a one-to-one mapping. Think of it like this. You take the text prompt, the model maps it to its internal representation, the hidden state. Injectivity means every different prompt gets its own unique hidden state representation, specifically looking at the last token state. There are no collisions, no two different inputs end up in the exact same numerical spot. And what's really fascinating, the paper argues this isn't some happy accident or something achieved through careful training. It's baked into the transformer architecture itself. It's there right from the start, at initialization, and importantly, it stays there throughout training, even with standard methods like gradient descent.
That really does sound counterintuitive. I mean, isn't the complexity, the nonlinearity part of what makes deep learning powerful, but also kind of chaotic and hard to predict? How can something so complex be proven to be so structurally ordered?
It comes down to how the analysis treats the transformer mathematically. The key insight is that its building blocks, things like the embeddings, the layer norm, the attention mechanism, the MLPs, even the residual connections, they all fall into a specific mathematical category. They're real analytic functions.
Real analytic. Okay, can you break that down a bit? Why is that the magic property here?
Essentially, real analytic functions are incredibly smooth, mathematically smooth. They don't have sharp points or jumps or places where the mapping suddenly collapses. It's this inherent smoothness that, mathematically speaking, prevents two different inputs from accidentally landing on the exact same output representation. This smoothness lets them use a powerful mathematical argument. Collisions, where two different prompts produce the same hidden state, can only happen if the model's parameters fall onto a very specific, incredibly thin set of values, a measure zero set.
Measure zero.
That sounds a bit like there's still a loophole, doesn't it? Like, okay, it's unlikely collisions happen, but maybe our current models just happen to be on that thin line. That's the beauty of the mathematical guarantee. Think of all the possible ways you could set the parameters of a giant LLM, like a vast high-dimensional space. A measure zero set within that space is so incredibly thin, it's like drawing a single line with an infinitely fine pen through that entire volume. The probability that standard random initialization methods like Gaussian or Xavier just happen to land the parameters exactly on that infinitesimally thin line is mathematically zero.
Okay. So the way we typically start training these models already avoids the danger zone, statistically speaking, and training doesn't push them into it either.
Exactly. Because the updates during training, like gradient descent, are also based on these smooth, real analytic operations. The training process itself won't move the parameters onto that collision-prone line. So the injectivity, the losslessness is preserved.
Right. The theory sounds solid, but they didn't just leave it at theory, did they? You mentioned empirical tests.
Oh, absolutely. They went to town on the empirical validation, really stress-tested this. They performed something like 5 billion pairwise collision tests. That means comparing the hidden states from 5 billion different pairs of prompts. And this was across 6 different real-world models, including GPT-2 variants, Gemma 3 models, Llama 3.18b, and Mistral 7b. Pretty standard, widely used architectures.
5 billion. That's staggering. It covers an immense range of possible inputs. You'd think if collisions were possible in practice, they'd find at least one. So what did they find?
Zero collisions. None. Nada. Across all those billions of tests on all models at all layers they checked. And it wasn't even close. The minimum distances they measured between the representations of different prompts were way, way larger than the tiny threshold they set for what would count as a collision.
Yeah.
Interestingly, they also found that in deeper models like GPT-2, the distance between representations actually tended to increase the deeper you went into the model. The layers seemed to amplify the uniqueness.
Wow. And they pushed it even further, right, with some kind of exhaustive test.
Yes, an exhaustive collision test focusing on continuations of prompts. This involved checking over 343 billion prompt pairs for each model tested. Even under that extreme scrutiny, the representations stayed clearly distinct.
Okay, so it seems undeniable. The theory says it's lossless, and the massive practical tests confirm it. Injectivity is real and robust.
Which logically leads to the next big question. If the information isn't lost, can we actually get it back?
Exactly. If it's structurally preserved, how do you retrieve it? This brings us to the algorithm they developed, SIPITE. That stands for Sequential Inverse Prompt via Iterative Updates.
Yes, SIPITE is clever because it directly leverages the transformer's causal structure. Remember how these models work, especially the decoder-only ones? The state at any given position, say position t,
Sure.
only depends on the tokens that came before it, the prefix, and the current token itself, sees data.
Right, so the past plus the present token determines the present state.
Precisely. And because of injectivity, if you know the prefix, the tokens up to $2, then the mapping from the possible next token to the resulting hidden state at position dollars is unique for each token in the vocabulary. SIPIT just exploits this step by step. It recovers the input one token at a time. To find the token at position dollars, assuming it knows the first $T tokens, it essentially tries out every single token in the vocabulary. For each candidate token, it calculates what the hidden state would be at position dollars. Since injectivity guarantees only one token will produce the actual observed hidden state, it just finds that match.
And because the vocabulary, while maybe large, is finite, this isn't some endless search. It's guaranteed to find the right token. How fast is it?
It's remarkably efficient. The paper proves SIPIT achieves exact recovery in guaranteed linear time. The complexity is proportional to the length of the sequence, times the size of the vocabulary, so times dollar steps in the worst case. That sounds like potentially a lot, but compare it to trying every possible sequence of length dollars that would be exponential, V dollar, which is computationally impossible. Linear time makes it practical.
That linear time guarantee is huge. It means this isn't just a theoretical curiosity. Reconstructing the input from hidden states is actually feasible. Did it work in practice? What were the recovery results?
Perfect. 100% accurate. They tested it on a mix of prompts, regular sentences, even sequences of random tokens to make it harder. And SIPIT reconstructed the original input exactly down to every single token every single time.
100% accuracy. And they compared this to other methods.
They did. They mentioned another method called heart prompts, which apparently completely failed to recover the true input in their tests, 0% accuracy. And a brute force approach worked, but as expected, was computationally prohibitive. SIPIT hits the sweet spot, perfect accuracy and practical efficiency.
So the information is there, and we now have a proven, efficient way to get it back.
Exactly. It confirms injectivity isn't just a mathematical property, it's an operational reality. The hidden states contain the full input, perfectly preserved.
Which takes us squarely into Section 4, the so what. If these hidden states aren't abstract numerical summaries, but basically just encrypted versions of the input prompt, what does that actually mean?
Well, from a scientific perspective, the researchers highlight this establishes a kind of clean baseline for interpretability. If you're trying to probe a model to see if it knows something and your probe fails, you can't blame it on the information being lost during processing. Injectivity guarantees the information is there, encoded in those states. If you can't find it, your probing method is likely the issue, not the model's representation. The states faithfully encode the full input.
Okay, that's important for researchers. But let's talk about the privacy implications. This sounds significant. If I use an LLM service and they log my hidden states maybe for debugging or monitoring, what does this finding imply?
It implies those hidden states are not just abstract data points. They are, as the paper puts it, essentially the prompt in disguise. Any system, any company, any process that stores or transmits those hidden states is, for all practical purposes, handling the user's raw text input itself. This kind of blows up the idea that internal model states are somehow fundamentally different or safer than the original text.
And this connects directly to things like privacy laws, right? Data dilution requests under GDPR, for example. Because regulators have sometimes made arguments based on reconstruction being hard.
Precisely. The paper actually calls out arguments like one reportedly made by the Hamburg Data Protection Commissioner in Germany. The argument suggested model weights might not count as personal data, partly because reconstructing specific training examples from the weights was seen as non-trivial.
Right, the focus there was on training data and weights. But this finding is about inference time, about the hidden states generated for your specific input when you use the model.
Exactly. And the reconstruction from those hidden states, generated at inference time for each user prompt, is now shown to be not just possible, but trivial and guaranteed exacts using SIPET. So the conclusion is pretty stark. There is no free privacy once data enters a transformer. If that hidden state exists, your input exists within it, fully recoverable. If the state gets logged or stored, your input effectively gets logged too.
So let's quickly recap this deep dive. The comforting notion that transformer LLMs naturally scramble and make input data unrecoverable. Fundamentally incorrect. Injectivity, this one-to-one mapping, is a core structural property. Hidden states are lossless. They contain the full input.
And we have the mathematical proof, we have billions of empirical tests showing zero collisions, and we have SIPET, a practical algorithm that demonstrates this invertibility with 100% accuracy in linear time. The model isn't losing your input, it's just translating it perfectly into numbers.
It really changes the mental model. We thought data went into a complex black box and got fundamentally altered, but it seems more like it goes into a glass box, perfectly preserved, and we just figured out the key to unlock it, or maybe just how to look inside properly.
And that leaves us with a really critical thought for you, the listener, to ponder. Now that we know these technical facts, that the representations are lossless and efficiently invertible, the big challenge is connecting this understanding with our rules and regulations. As the paper suggests, the crucial next step is bridging these technical insights with evolving regulatory frameworks. If the data being handled isn't abstract but is effectively raw text, how do our policies for privacy, security, and data handling need to adapt to ensure these incredibly powerful models are deployed responsibly?
A very important question indeed. That's all the time we have for this deep dive. Thanks for joining us.